Okay, in this segment, we're going to talk about our next amplifier. It's called the current mirror differential amplifier. And like the simple 5-transistor differential amplifier, we're going to start out with our NMOS stiff pair. So we have a V1 and a V2, and an M1 and an M2, and an MB, common source node. We have an I1 and I2. And then instead of connecting just one current mirror to the drains of these transistors, we're actually going to take two PMOS current mirrors and one of them is going to turn around I1, and that one will be M3 and M4. And then second one we're going to use to turn around I2, and that'll be M5 and M6. And then we're going to take this turned around version of I2 and we're going to turn it around again with an NMOS current mirror. And we'll call this M7 and M8. And we could call this voltage here, say V3, V4, or the V5, let's say the gate voltage of diode connected M5. And we could call this one, don't like that ground symbol. We can call this gate voltage here V7. This is going to be our output. And we will define our output current, if there's any flowing out of the amplifier, as positive coming out of the amplifier. And so we have here I3, I4, I5, I6, I7, and I8. So I think it should be fairly obvious why this would be called a current mirror differential amplifier. It's basically a bunch of current mirrors. And conceptually, this circuit works in a very similar way to our 5-transistor differential amplifier. So if you remember, one thing that we did is we said, suppose we have a voltage source that we're going to attach to the output to hold the output voltage fixed at a place where both the two output transistors, in this case M4 and M8, are both saturated. Okay, so M4 V out is somewhere that makes M4 and M8 both saturated. Okay? And we want to know, what is I out? Okay, we're going to make all of our standard assumptions, right? All the NMOS transistors are matched to each other. All the PMOS transistors are matched to each other. They're all operating at the same temperature. And we're going to, for the time being, assume the early effect is negligible. So these are our standard 0th order assumptions. And we want to know, what is I out for this amplifier? Well, let's see. Well, we know by applying Kirchhoff's current law at node V3, so KCL at V3 implies that I3 will equal I1. KCL at node V5 tells us that I2 is equal to I5. KCL at V7 implies that I6 will equal I7. Okay, and the KCL at the output tells us that the sum of the currents flowing in is equal to the sum of the currents flowing out. So we have I4 is equal to I out plus I8. We can rearrange that to solve for I out. And I out is going to be I4 minus I8. Well, I4 is just a mirror copy of I3, which is equal to I1. And so this is equal to I1. And then I8 is a mirror copy of I7, which is equal to I6, which is a mirror copy of I5, which is equal to I2. So our output current is once again just the diff pair's differential output current. So we have the diff pair that takes V1 and V2, the two input voltages, and transduces that into a pair of currents. And we've studied that, and hopefully we'll have a good understanding of that to build as a foundation at this point. And then we have some current mirrors that are going to take those two currents and make them face off together at the output in such a way that the output current of the amplifier is just I1 minus I2, which is exactly the same thing as it was for our 5 transistor diff amp. Okay, but so you might wonder, why is this better than the 5 transistor diff amp? Why might we want to use this over that simpler circuit? Obviously this one has 4 extra transistors in it, and so is roughly twice as complex as our 5 transistor diff amp. This is a 9 transistor diff amp instead of a 5 transistor diff amp. Well, I think the easiest way to explain the advantage that this circuit has relative to the 5 transistor one is to flip over to the simulator. And here I have basically prepared our current mirror differential amplifier and our 5 transistor differential amplifier, just like you had in Lab 8. And what I'm going to do is repeat experiment 1 from Lab 8 on both of these circuits. So I'm sweeping V1 from 0 to 5 for several values of V2 that are kind of spaced out. So for fixed values of V2, I'm going to start at 1.5 and go 2.5, 3.5, and 4.5. And we're going to look at sort of the large scale voltage transfer characteristics of these two circuits. So simulate, and then tile these vertically, thank you. And if we look at V out of the 5 transistor diff amp, you see these voltage transfer characteristics that have this kind of creeping up lower limit. Okay, so while the 5 transistor diff amp is able to have its output go practically all the way to the positive supply rail, it doesn't get nearly to the negative supply rail. And so this amplifier, the 5 transistor diff amp, does not have what we would call a rail-to-rail output voltage swing. So the region or the range of voltages that the output will move through in its high gain region is limited to some fraction of the power supply rail, or the power supply, the difference between the two power supply rails. And that is almost rail-to-rail for kind of low common mode input voltages, but as you get higher and higher on the common mode input, that range gets more and more restricted. Whereas if we were to, say, repeat the simulation, and let's click on V out here, you can see that for the 9 transistor diff amp, regardless of where our V2 input is, whether it's down near 1.5 or up near 4.5, this amplifier's output basically goes from almost the ground rail to almost the VDD rail before it starts rolling over and saturating. So the high gain region extends nearly from rail to rail, basically one saturation voltage above the ground rail to within one saturation voltage below the VDD rail. And so this amplifier, the current mirror diff amp, has what we would call a rail-to-rail output voltage swing. Okay, that makes it attractive for many applications that the 5 transistor diff amp by itself would not be attractive for. So we want to get our heads around kind of how this circuit works and what its properties are. So we were going to go through a number of analogous sort of calculations for this differential amplifier as we did for the current mirror diff amp. And the first thing to do is to think about what is the quiescent output voltage going to be for our circuit for a pure common mode input. Okay, so if we were to take away that output voltage source that's holding the output voltage fixed, and we were to let's take away these current arrows. So we're going to assume that V1 equals V2 is some pure common mode input. We want to know what is V out. Well, in this condition, we know that we're going to have half IB flowing through the diff pair and through M3 and M5. Okay, so that means that the current through M3 is going to be equal to the current through M5, and that suggests that V3 is going to have to equal V5. These are both matched transistors. Their source voltages and bulk voltages are the same, and they are diode connected. And so in order for them to be passing the same current, they're going to have the same gate voltage in addition to the source and bulk voltage. So M3 and M5 are matched. Same source, bulk, diode connected. which implies that they're saturated. So this will in turn imply that they must have the same gate voltage. Actually, these are operating at the same current. And that will imply altogether that V3 is equal to V5. So here we have V3 and V5 basically equal to each other. They're not shorted together, but by the symmetry of this sort of input stage here, if we break the circuit up into sort of the diff pair plus the two diode connected transistors on the input side of the circuit to the left, and an output stage which is sort of M4, M6, M7, and M8, we have these two voltages that connect the input and the output house of the circuit are going to be equal to each other by symmetry, really. Well, we have a situation here where we have M6 and M4, they are going to be producing the same current. So let's call this I6 and I4. So I4 and I6 are going to have to be the same if there is no early effect. If there were an early effect, then we could say some things about I4 and I6 because the gate voltages are the same. They're going to be operating on the same drain characteristic. So with early effect, we can say that if V7, let's say V out, is less than V7, so V out is below V7, that will imply that I4 is going to be greater than I6, right? Because this transistor will have more voltage across it than M6 and will be biased further into saturation, and because of the early effect, I4 will be somewhat larger, not too much larger, but slightly larger than I6. If V out equals V7, then I4 will equal I6. If V out is greater than V7, well then we have I4 is less than I6. Okay? Well, M6 or M7 and M8 are, so we call this I7 and I8. It's not a very good looking 8. I7 and I8, they form a current mirror. And we can say, because these two transistors will be operating on their same drain characteristic, we can look at the same inequalities on the voltages here. So if V out is less than V7, well, that means that I8 will be less than I7. That means that V out being less than V7 means that M8 will be biased closer to the ohmic region than M7. They'll both be saturated, perhaps, but I8 will be less into saturation than I7, or M8 will be less into saturation than M7. If V out equals V7, we will have I8 equals to I7. And if V out is greater than V7, that means that I8 will be greater than I7. Well, KCL at V7 implies that I6 will have to equal I7 in a steady state once any transients maybe have settled out. And so we can combine these inequalities here to find that, so if V out is less than V7, we have I4 is greater than I6, which equals I7 is greater than I8. V out equals V7. We have I4 equals I6 equals I7 equals I8. If V out is greater than V7, we'll have I4 is less than I6, which equals I7, which is less than I8. And so this one implies that I4 minus I8 is going to be greater than 0. This one implies I4 minus I8 is going to be equal to 0. And this one implies that I4 minus I8 is going to be less than 0. Well, KCL at V out, remember, implies that I out equals I4 minus I8. Right, so we have if V out is less than V7, we have I out is greater than 0. V out equals V7. I out equals 0. And if V out is greater than V7, we have, looks like an 8, doesn't it? We have I out less than 0. So what that tells us is that in this pure common mode input situation, V out is going to operate at whatever voltage V7 is. Okay, with a 5 transistor diff amp we had V out was going to basically mirror the voltage value that was on the gate of M3. Well, with this configuration, V out is going to basically do whatever the voltage here V7 does. Okay, because that's where the current I out is going to be equal to 0. Okay? So basically V out will equal V7. So the question is, do we know anything about V7? Well, we know that M7 is diode connected, and it's carrying a current that's going to be on the same order as the bias current. It's actually going to be a little bit more than half the bias current. So we have half the bias current here. We're going to mirror half the bias current through these two current mirrors. And so without any early effect, I7 will be half of IB. But because of a finite early effect, we're going to have a systematic transfer error with these two current mirrors, so that the current I6 and I4 will be a little bit bigger than IB over 2, but not twice as much. So it's going to be probably somewhere between IB over 2 and IB. Might be like 10% more, something like that. And so V7 should be very nearly the same as VB, because M7 is matched to MB and is carrying about the same current, so it's going to need about the same gate to source voltage as MB to pass that current. It's going to be a little bit less than IB, or rather MB, VB, because it's not carrying exactly the same current, but it doesn't take very much change in the gate voltage to make up a factor of 2 roughly difference in the currents, right? If you remember, it's a very steep IV curve, and in weak inversion it would be less than 25 millivolts to make up a difference in, well, might be 25 millivolts given the kappa, to make up a difference of a factor of 2. That's not very much. So if VB is around a threshold voltage, V7 will be a little bit less than a threshold voltage. It'll be maybe a few millivolts, 10, 20 millivolts below VB. So we would now be in a position to figure out the common mode gain, based on a similar argument to the one we used to figure out the common mode gain of our 5-transistor diff amp. So if we change VCM by delta VCM, so if we add a delta VCM, what we're going to have is an increase in the common source node voltage by delta V. That'll generate an increase in IB by a delta IB. That increase of delta IB will be split evenly between the two halves of the input part of the circuit. So it'll be a delta IB over 2 increase here and here. Those will get mirrored. So we'll have IB over 2 plus delta IB over 2 flowing in this branch, and a IB over 2 plus delta IB over 2 flowing in this branch, and that will give rise to a plus delta V7 and a plus delta V out. And so we can write down the delta V as kappa times delta VCM. Again, the diff pair in common mode is like a source follower, and so the incremental gain from the gate to the source will be kappa. And the increase in the bias voltage will be that little bit of increase in voltage across the early effect resistor of MB divided by ROB. So delta IB will be delta V over ROB, which is equal to kappa times delta VCM over ROB. So the delta, say delta I3 or delta I1 equals delta I2 equals delta I, say 6, and delta I 4 is going to be equal to 1/2 of delta IB. And so that will be equal to kappa over 2 times delta V CM over ROB. And the delta V out will equal to delta V7, which is going to be the delta I6 divided by GM7. The GM of this diode connected transistor is going to be the amount by which the gate voltage has to increase to accommodate the extra increase in the saturation current. And so the delta V out is going to be basically kappa over 2 times delta VCM over GM7 times ROB. And so ACM is going to be the delta V out over delta VCM, and that should be kappa over 2 times 1 over GM7 times ROB. Notice that we have here that something that's on the same order as our 5 transistor diff amp common mode gain. It's a kappa over 2 times a GM RO. In this case, it's a GM of this diode connected transistor here times the RO of this bias transistor. These are both NMOS transistors. Their currents are tied together by roughly a factor of 2. And so this GMRO is going to be something like the intrinsic gain of an NMOS transistor. And so we would expect this number to be something on the order of something like 0.01, maybe 0.005, something like that. And notice it has a positive sign. So whereas the voltage on the diode connected transistor, the PMOS diode connected transistor of our current mirror diff amp, or our 5 transistor diff amp, came down so that the common mode gain was negative. In this circuit, the common mode gain is positive. And so we can flip back over to LT Spice if we like, and we could, I guess we could switch this to V1, and that would make this a pure common mode input. I can switch this to V1, and I can add the simulation command to get rid of that. And now if I run the simulation, we can see the common mode behavior of the 2 circuits. So these are common mode voltage transfer characteristics, and you can see that once we get up into the range where the bias transistors are operating in saturation, which is roughly, for a bias voltage of 8 volts, it's going to be 0.8 plus VDS sat over kappa, which is going to take us up to about 0.9. You can see that the output voltage here is roughly a little bit below 0.8, and it increases slightly. You can see it increasing by a few, like 1 pixel here. Whereas for our 5 transistor diff amp, we're about a VB below VDB, and we can see it has a slight negative slope. You can see it comes down by 1 pixel up here. And if I were to zoom in, we can see here Here the output is changing by, let's say, roughly 2 volts, from 1.2 to 3.2, and we can see that the output voltage is increasing by, see, 740, say 742 to 745, 745 millivolts. And so that's roughly a 3 millivolt change for 2 volts. Common mode voltage input change. And so that's going to be a gain of 3.003 divided by 2, which is going to be about 0.015. 0.0015? Alexa, what is 3 thousandths divided by 2?
3,000 divided by 2 is 1,500.
That's not very helpful, Alexa, sorry. Let's see. 0.0015. Yep, okay. If we zoom back out, and we look at this one, we can see that we're changing from, let's say, 4.08 to at 1.6, and at 3.6 we're down to 4.078 roughly. And so that's a difference of 278. So 82 minus 78 is 4. So it's minus 4 millivolts in 2 volts. So it's like 0.002 as the common mode gain, and it's negative, like we said it was. We can also, if we like, zoom back out and click on this node here. You can see that that node, the internal node V3 of our 5 transistor diff amp, is basically exactly the same as the blue. Can't distinguish them. And if we were to click on node V7 of our current mirror diff amp, you'll notice that this cyan curve here is covering up the green curve, indicating that Vout is basically doing exactly what V7 does. Okay, so it all checks out in the simulator. So what we've kind of reasoned our way through, assuming ideal matching and finite early effect, is all pans out in the simulator where we have ideal matching. Okay, so I think that's all we're going to talk about right now. In the next segment, we'll talk about the differential mode gain. We'll find that this circuit also has a very similar differential mode gain to our 5 transistor diff amp. So we'll see you in class on Tuesday.